Right, this is the AP Chemistry lesson for day 50. This is on bond energies, and I'm going to go ahead and give you the solutions to these. It's due on Wednesday. So the first one is the one we did in class, and we're going to go ahead and do that for you on this sheet. So it's to compute the enthalpy of reaction, which is also an enthalpy of combustion since it's a combustion reaction. So it can be called different things for methane using the bond energy method. First, write the balanced equation. So I've already given you a balanced equation there, and I've given you diagrams of the Lewis dot structures of each of the compounds. You're going to need that because you need to know what type of bond that we're dealing with here. So what it's saying is we have one methane molecule here in the balanced reaction. So that means we have 4 carbon-hydrogen bonds. So that becomes 4 times the carbon-hydrogen bond, if you go to the green sheet, is 413. And that's going to give us a number of 1,652 kilojoules. Now that's a positive number because, and you might want to write this down, to the reactant side, the numbers are positive. Because energy has to go in to break the bonds. And on reactant side, energy is negative. Okay, so we've got that for methane. Now we go to oxygen, and we go to O2. Now you have to know that O2 forms a double bond. You're going to learn how you know that later this week, but for right now I gave you a diagram to show it to you. So you have you have one double bond between the oxygens, but you have 2 oxygen molecules. So that means it's 2 times, and you come up here and you find the oxygen double bond right there. Be sure not to use a single bond, use the double bond, and it's 495. And again, that's energy going in. So 495 is going to equal 990 kilojoules. And again, it's a positive number. Okay, next we have carbon dioxide. And there's 1 carbon dioxide. Each carbon dioxide, though, has 2 carbon-oxygen double bonds. So we need to have 2 times the energy of a carbon-oxygen double bond. There it is, 799. And that's going to equal 1,598 kilojoules. Now that's going to be negative. The reason it's negative is because when bonds form, this is on the product side, and when bonds form, they release energy. They tend to go to a lower energy state, and that releases energy. Finally, over here for water, you have 2 oxygen-hydrogen single bonds, one there and one there, but you have 2 water molecules there. So that's a total of 4, 2 in each of the 2 molecules. So it's 4 times, and you look for oxygen, hydrogen, single bond right there is 463. And that again is going to be releasing energy. And that's going to be 1,852. Right there. So what your equation is the really the way to view it a little bit differently than I said. It's the products, the energy of the products, which is going to be a negative number, plus the energy of the reactants, which is going to be a positive number. So as long as you remember that's a negative number, you can just call it E products plus E reactants. Okay, and that's going to give us, so we add these 2 numbers together and we're going to get a bigger negative number. Okay, it's negative 3450. And over here, we have 1652 plus 990, and that's going to be 2642. And so you add those two numbers together and you end up with a negative 808. I think it sure is. And that's kilojoules. It says it's for 1 mole. If you want, you can say it's per mole. But it doesn't always have to be for exactly 1 mole. It just happens to be in this case, okay? So that's how you do that. Now let's use the enthalpy of reaction method. So you've done this one before. Actually get the enthalpy of reaction using the enthalpy of formation method, okay? So that's the purple sheet. So pull out your purple sheet. Okay, so let me come on down here where I was talking about. So calculate the enthalpy of reaction for methane using the enthalpy of formation method. So you're going to use this sheet. It has enthalpy of formations for all of these. You don't have to write out the formation reaction. You just have to get the number and do this. So the formula for this is that the delta H of reaction using this method is equal to the sum, sigma, big sigma is the summation, and you have to put the number of moles times each of these numbers, and it's going to be the delta H of formation, delta HF of products, minus the same thing for the reactants. Okay, so let's go ahead and do that. So what are the products and reactants? We can come back up here. So the products are CO2 and 2H2O. So it's going to be 2 times, or excuse me, CO2 is 1. So again, I used my big block brackets there. And CO2 has an enthalpy of formation of negative 393.5. There's 1 mole of it, so I don't need to put anything in front. And then you're going to add to that the 2 moles up at the top for water. And water has the, and we are going to say, I didn't specify, but we are going to say that's going to be of a gaseous water. So that's going to be negative 241.8. Okay, the process is more important than the exact number there, so go ahead and use whichever you want. I think I told you in class, but we'll do that. Now you're going to subtract from that the enthalpy of formation of the reactants and CH4. We have 1 mole of that, so we come over to the sheet. That's methane, and there it is, methane, CH4 gas is negative 74.8. And we've actually done this problem before, but it's fine to do it again. And then the enthalpy of formation for any pure element like O2 is always defined as 0. So that's a principle to remember there. Okay, and now you're going to go ahead and put all these together. Okay, and for this I get negative 877.1, and that's going to be plus the negative, minus a negative is going to be a plus, so 74.8, and if you do that, you get 802, close enough for us. Again, remember, bond energy is just an approximation. Enthalpy of formation is actually a more accurate method, and that's kilojoules for that reaction. Okay, so there's your answer compared to that, pretty close to each other. All right. Okay, now we're going to do the same thing for ethane, C2H6. In this case, I left you to balance the reaction. So I hope you're getting good at these balanced reactions. I would like to really see you at this point move beyond the box method. So let's go ahead and balance this. It's not too hard, and combustion reactions kind of have the same series of steps. So we have 2 carbons on this side and 1 on this side, so I'm going to make that a 2. So now our carbons are in balance. Now that also affects this oxygen, but we don't want to deal with oxygen simply because it appears as a pure element, so you want to leave that till last. And it also appears in two locations on the right-hand side, so leave it alone. So let's go on over to hydrogen. So we have 6 hydrogens here, we have 2 hydrogens there. We have to multiply this by 3. So now we have 6 hydrogens, 6 hydrogens. So now we look at how many oxygens we have. We have 2 times 2 is 4, and 3 times 1 is 3. 4 plus 3 is 7. So you simply have to ask yourself, you need 7, and you have a 2 here. So what do you have to multiply 2 by in order to get 7? And the answer is 7 halves. So the 2's cancel and you end up with 7. So this coefficient is 7 halves. This one is 1, this one is 2, and this one is 3. Now, it's a little messy dealing with fractions with these, so I'm going to go ahead and multiply through by 2 to iron out that denominator there. So we end up with 2, 7, 4, multiplying all the coefficients by 2, and 6. So we'll go ahead and work with those, okay? So let's go ahead and do this. So again, we have in an ethane, we have 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So I'm going to write carbon-hydrogen right here. And we have 2 molecules of that. Let me erase some of these other numbers so it's not confusing. Okay, so we have 1, 2, 3, 4, 5, 6, and we have 2 molecules of ethane, so that's going to be 12. 2 times 6 is 12. And then each carbon hydrogen, go back to your green sheet, is 413. That's a positive number because the energy has to go in to break the bonds. So we have that, and then we have carbon-carbon. Okay, and we have one of those, but we have 2 molecules. So we have 2 carbon bonds, and carbon-carbon is right there, is 348. Okay, so what we're going to do is 12 times 413 plus 2 times 348. And that gives us 5,652 kilojoules. Okay, now for oxygen, we have a double bond of oxygen, and we have 7 of those. So we have O double bonds. There's 7, and you multiply that by this number right here. There's oxygen double bond. Don't use the single bond. It's 495. And what does that give us? 3465, and again, these are positive numbers. So when you add those 2 numbers together, you get 9,117 kilojoules. So that's the energy taken to break all of the bonds on the reactant side. Now we're going to go over to, I'll draw a little line here, we're going to go over to the product side. CO2. So CO2 has 2 double bonds between carbon and oxygen. There's a carbon-oxygen, there's a carbon-oxygen, there's 2 in each molecule. And it says you have 4 molecules. So how many different CO double bonds do you have? You have 8 in all. 2 in each molecule times 4 molecules. And we come over to our sheet here, and CO double bond is 799. So that's going to be 6,392 kilojoules. Okay, and then water. Each water molecule has 2 hydrogen oxygen, so those are HO. And each one has 2, and there's 6 of them. So 6 times 2 is 12. And that's going to be times HOOH. It doesn't matter whether you write it HO or OH. Either way is fine. And that's 463. Okay, so that's 12 times 463. and that gives us 5,556 kilojoules. And what I neglected to add, the first case, was that's a negative. When the bonds form, energy is released. The molecule goes to a lower energy state. So you're going to add those two together. And that's going to give us negative 11,948 kilojoules. Now you simply add these two sides together. Remember to keep the negative sign there. And that's going to give us an answer of negative 2,831. So this reaction is exothermic, and it releases 2,831 kilojoules of energy. Now, if you wanted to know how many kilojoules per mole of ethane, notice that we have 2 moles there. So if we want the, that's the delta H. And if we want the standard delta H, this is of reaction, standard delta H, that would be per mole. You'd simply divide that by 2, because this is the amount we got for 2 moles. So I'm going to divide that by 2, and that'll give us 1416 in round numbers. And that's kilojoules per mole of ethane. Okay, not too bad, is it? All right, let's do the same thing with enthalpies of formation, see what we get. So enthalpies of formation, one of the reasons we did this at the end is because enthalpies of formation are for 1 mole. So what we're going to do is we've got ethane, and you look at your sheet there, and there it is, and it's negative 84.6. Whoops, I'm actually doing this in the wrong direction. So let's go. We need to do products first. So carbon dioxide, and we're going to do this reaction here with these coefficients, but remember we have to get back to 1 mole at the end, so we're going to have to divide everything by 2, just like we did there. Let me make it clear what I did there. I divided by 2 moles. Okay, the 2 is because of the 2 moles right there. All right. All right, now let's go ahead and do this, and it is going to be, well, I tell you what, let's just do it, yeah, let's do it with 2 moles. Okay, so we got 4 moles of CO2, so there's my big block, 4, and CO2, excuse me, is negative 393.5, plus we have 6 of water up here. Just a little there so you can see it. Okay, 6 of water there, so it's 6 times, and we okay, didn't specify, I guess. I can't remember what we used last time, but let's go ahead and just say that that's going to be 241. You use 285, it's fine. Again, it's the process more than the exact number, and if we had specified, there wouldn't have been any question about it. Okay, and then it's going to be minus, and we need it for ethane, and the enthalpy of formation for ethane is negative 84.86. Okay, plus, and it's 7, but it's 7 times 0, because for oxygen it is 0 enthalpy of formation for a pure element. So now we're going to go ahead and multiply that out. So okay, and for this we get negative 3024.8, and now we're going to add this to it up here. And we get plus 84.86. And that gives us negative 2939, or let's just round it to 40. 2940. Again, though, that was for 2 moles of everything, so that's kilojoules. And if we want kilojoules per mole, we divide that by 2. and we get negative 1469 or 1470 kilojoules per mole. You compare that with this, you might have found, probably did if you used the other state. We used gas. If you'd used liquid, it might have been a closer number. Let me get so you're on screen here. So this is what we got for this. That's what we got up there. They're not that close together, but if we had used liquid water, it might have been closer. I don't know. So anyway, they're close enough though. It's only off by about 50. So that's how you do those. All right, they should ideally give you the same answer, but again, bond energies is only an approximation. Okay, and in problem number 3, I'm only going to ask you to do the bond energies, not the enthalpy of formation method. So first you have to balance the equation. You have 3 carbons and 1 carbon, so you got to put a 3 here. Again, you don't want to mess with oxygen, so let's just go ahead to hydrogens. So you have 2 here and 8 here, so we're going to, and that balances hydrogen and carbon. So now how many oxygens do we have? We have 3 times 2 is 6, and 4 times 1 is 4. So 6 plus 4 is 10. So we're not going to end up with a fraction this time. So it's going to be 5 there. 5 times 2 is 10. You got a 3 there. You got a 4 there. And you have a 1 here. So whatever we get is going to be our per mole number, or our enthalpy per mole number, okay? All right, so go ahead and do this. So you have, let's look at this one. So you have 1, 2, 3, 4, 5, 6, 7, 8 carbon hydrogen bonds. So I'll put that here. And there's 8 times 413, and that's energy going in, so it is positive. And then you have carbon-carbon bond, single bonds, and there's 2 of those, 1, 2 carbon-carbon single bonds. So 2 times, and again, go back to your sheet, it's 348 right there. And now we just add that whole thing up. And that gives us exactly 4,000. Okay, now we have 5 O2. So we have an O2, a double bond. Each molecule has 1 double bond. So there's 5 molecules. So for OO double bonds, it's 5 times. You come over here, right there is 495. Again, these are positive numbers because they're energy going in to break the bonds. And that's going to be 2,975 kilojoules. Okay, and there we go. So you're going to add those two together. That's pretty easy. That's going to be 6,975 kilojoules. Okay. All right, now we come over to the other side, draw a line there. And for carbon-oxygen double bonds, it's going to be, there's 2 of them in each molecule, and it says you have 3 molecules. So 3 times 2 is 6 times, and the value of the bond, or the amount of energy required for the bond, it's a double bond, is 799 right here. And it's 4794 kilojoules right there. And finally, for water, we have 2 hydrogen oxygen bonds in each molecule. We have 4 molecules, so that's 8 times, and the hydrogen oxygen is a 463. Again, that should be a negative there because it's energy coming out as these compounds are put back together. Okay, and that's going to be negative 3704. So So when we put those two together, we get negative 8498. And when we add those two together, we get negative 1,523. That's kilojoules, and it is per mole since there's just 1 mole of propane up there. Okay, so that's your final answer for that. Okay, so this is the number 4 is the Hess's Law problem that we did in class. I asked you to write in your notebook. See if you can do it now without looking at your notebook. But if you can't, you've got your notebook to use as a reference. So again, what we're trying to do is arrange these equations by either reversing them, multiplying through by a factor, or doing additions of compounds on the same side, subtractions if they're on opposite sides. So you got those 3 things that you can do. And what we're trying to do is match this reaction. So the strategy for these is simply to pick an element or compound that only appears once down here somewhere. So we got a couple of candidates. H2 only appears once, and it's up here in our final reaction as well. C, graphite, carbon solid, only appears once, and it's up here. And finally, C2H6 only appears once, and it's up over on this side. So let's start with the carbon graphite. And since it's on, I like to circle my arrows to be sure I'm really clear which side is which. So since carbon graphite is on the left side of this arrow, and for our final reaction that we're trying to match, it's on the left side of this arrow, we don't want to reverse this equation. We want to keep it like that. However, there is something we need to do to get this carbon to be like this one. This one has a 2 and this one only has a 1. So what we're going to have to do is multiply this entire equation through by 2 so that we have 2 carbons there, okay? So I'm going to just put a little times 2 here, and that goes for everything. So I'm going to put a parentheses around the entire reaction, including the enthalpy over here. And everything here gets multiplied by 2. So I'm going to come down here, and I keep track of my equations. I'm going to label this 1A. Do this however you find it best to keep it organized. For me, this is the way to do it. So we have 2C, and that's graphite. Okay, plus we have 2 times O2, so 2O2, and that's a gas. And then we have our arrow, and we have 2CO2. And that's a gas. Now, the whole point of this is we now want to multiply the enthalpy by 2 as well. And that will give us, for this reaction, a delta H equal to 393.5 times 2. And that's 787. It is a negative. Don't leave the negative off. 787. Okay. Now let's find something else that appears only once. And we said that, by the way, I'm going to put a light line through this so I don't make the mistake of using it again. Okay. All right. How about hydrogen? We said that appears only once. And it appears on the left side of this arrow. And the hydrogen up here in the final target equation appears on the left side of this arrow. The difference is this one is 3 moles and this one is 1 mole. So we're going to do something similar to what we just did for carbon. We're going to multiply by 3. So 3 times everything in this reaction here. We're going to bring that down here, and we're going to call that equation 2A. So I've got 3H2 gas plus, now it's 3 times 1/2 here. So that's going to be 3/2 O2. Gas, and that's going to bring you over here and give you 3H2O, and that's going to be in liquid form. Okay, and remember that's not a 1, it's an L, it's a lowercase l for liquid. So now we have to multiply this by 3 as well. And that gives us negative delta H of reaction for that now becomes negative 857.4. I'm just going to call it 857, okay? All right, so we've taken care of that. So we've taken care of two of the three things that appear in our target. We've taken care of the hydrogen and the graphite. So now we've just got this one. So where do we see C2H6? Well, it's in equation number 3 is the only place it appears. And there's two issues with it. One is it's on the left side of the arrow here in this equation. We need it to be on the right side of the arrow. So we're going to have to reverse everything in this equation here. The second issue is there's only 1 mole there, but there's 2 moles there. So we're going to have to multiply by 1/2. We're going to have half of that number to be there, okay? So I'm going to do both of those in one big move here. So let's look at what we got. We're going to move everything on this side over to the left side. So here we have 4 carbon dioxides. They're going to move over to the left. And I said I needed to, I'm going to go ahead and write it here, multiply everything by 1/2. So 1/2 times both of these things. And then over here, I'm just going to write a reverse arrow here. We're going to reverse everything. We're going to switch everything around. So let's first just do the multiplication. 1/2 of 4 is 2. And then I'm going to move the 2 carbon dioxide over to this side. So this becomes equation 3a. Okay, so I've got 2 CO2 gas. Okay, plus, now we go to the water. I need to cut that in half, so 6 goes down to 3, and then I need to move it over to the other side. So I got 3 H2O liquid. And now my arrow. And we have 2 C2H6. I'm going to cut that in half so that we just have 1. And I'm going to move it over to the right side. And that's the whole reason we did this, is so it would match up with that up there. So we have 1 C2H6. I'm just going to leave the coefficient off. That's gas. And then finally on this side we have the 7 O2s. And so we're going to divide those or multiply those by 1/2, and that's going to be 7/2, and it moves over to this side, 7/2 of O2 gas. Okay, so now be careful. What happens to this? I'll write it down below so I have a little more space. Delta H of reaction. 2 things are going to happen to it. Since we reverse the equation, the negative becomes positive. And since we multiplied everything by 1/2, we multiply this by 1/2. So we start off with a positive 3119.6 because we changed the sign. That was reversing the equation. And now we're going to divide that by 2 or multiply by 1/2, or however you want to put that. And that's 1560, and it's a positive number. Okay, so now we're not quite ready to add these or subtract these numbers yet. We got to see if everything works out here. So we've canceled all 3 of these original equations because we changed them in some way. So let's see, we got 2C here and we got 2C there, so the graphite works out. We have 3H2 here and 3H2 there, so the hydrogen works out. And over on the right-hand side, we have 1 mole of C2H6, and we have 1 mole of C2H6. So everything that I've circled appears up here. What that means is that everything else that I didn't circle should cancel. So let's start with the easy ones. 3H2O on the right and 3H2O on the left cancel out. 2 CO2 on the right and 2 CO2 on the left cancel out. The last one might be a little trickier. You got 2 O2s, 3/2 O2 on the left, and then you got 7/2 O2 on the right. So 2, if you express it as a fraction, with 2 as the denominator, 2 equals 4 over 2, and that's O2. So that 2 becomes 4 over 2. Now we're going to add it to the oxygen on the same side, and that's going to be 3/2 O2. And if you add those together, you get 7/2 O2. So these two become 7 halves O2. They cancel out with the 7 halves O2. So everything has canceled out. So we know the equation is set up properly. Now we're ready to go ahead and add these numbers. And so you can take 1560 or 59.8 if that's what you stuck with. And then we're going to subtract 857 and we're going to subtract 787 and we get negative 84. So the delta H of reaction for that reaction up there, which is, by the way, a formation reaction because you have basic elements giving a compound. So you can call it a delta H of formation if you want. And that's going to equal, and it's a negative number, negative 84 kilojoules, and since it's a formation reaction, it's for 1 mole of the ethane, so it's per mole. Okay, and there you go. All right, let's do another one. This one's from your textbook. I think the last one was too. This one's problem 5.63. I did a bad job down here of not doing my subscripts properly, so let me do that so it's more readable. So it's C subscript 2 H4. Ethylene plus 6, and that's F subscript 2, and I should put gas and gas. So I'm just changing these numbers to subscripts like they should have been. And then it's 2CF4 gas, and then it's 4HF. Okay, so let's balance all of that. Okay, so let's go ahead and balance this reaction. So we have 2 carbons and we have 2 carbons. So carbons in balance. We have 4 hydrogens and 4 hydrogens. So hydrogen is in balance. 6 F2s. Yeah. So we have 6 F2s. So that's 12. 6 times 2 is 12. You write that like looks like a 6. Over here you have 2 times 4 fluorines, that's 8, and 4 times 1, that's 4. So 8 plus 4 equals 12, so that balances. So the reaction is already in balance. Okay, so let's go ahead and work on this to try to make this look like that. So let's find something that only appears once, and we could pick a lot of things. Let's see. Let's start off with CF4. That only appears once, right? Yeah. So this CF4 right there, and there's CF4 up there, and it's on the same side of the arrow. So if you want to simplify your life, if you want, all you got to do is multiply by 2. You could go ahead and just multiply these by 2 and multiply that by 2 right there. But again, I like to write a separate equation, just keep things laid out here. So this is equation 2a. And what we're going to do is multiply by 2. Again, why are we doing that? Because we have CF4 here. We need to shoot for 2 CF4s. So we're going to have to multiply everything by 2. So we end up with 2 carbon solids plus 4 fluorine gas, diatomic molecule, 4 F2 gas, 2 times 2. Then you have an arrow. And then you have 2 CF4s. That's a gas. And now finally you're going to multiply this by 2, and that's going to give you a delta H of reaction, and that's going to be negative 1360 kilojoules. Okay, so we've taken care of this equation right there. And we've gotten this to match up with this. All right, now what else? So we still have this equation, and this equation. And let's look at, what am I going to look at? I'm going to look at C2H4. So here's C2H4, and here's C2H4 up here. It appears on the right side of this arrow, and I didn't circle my arrows like I told you I like to do. Okay, so it appears on the right side of this arrow and it appears on the left side of this arrow, but it's 1 mole in both cases. So that means all I need to do is flip the equation, reverse the equation. So I'm going to come down here and do that. Okay, and I get C2H4, that's a gas, and then an arrow, and then I got 2C solid on the right side plus 2H2 gas on the right side. So all I'm going to have to do with this number right here is change the sign. I didn't multiply by anything, I just reversed the equation. Okay, so that's going to be negative 52.3 kilojoules. All right, okay, so I've taken care of this equation. So let's see where we stand right now. HF. We still have this equation. And let's see, okay, so 2 HFs are on the right side of the arrow and 4 HFs are on the right side of this arrow. So what I'm going to need to do is multiply this equation by 2 because I need to get the HFs to be 4. So 2 times 2 is 4, and that's what I have up here. So I'm going to go ahead and write this down here. That's equation 1A. And it's going to be 2 H2s, gas, plus 2 F2, gas, and that's going to give us 4 HF. Yeah. And that's gas as well. So since I multiplied through, I didn't reverse the equation, I just multiplied everything through by 2. So this is going to be 1074 for delta H of reaction. And that's kilojoules. Okay, so let's see where I stand. I've got my 2 HFs and my 4 HFs and my 4 HFs. Or actually, I should put a line through this one. So I've used all 3. So now I'm down dealing with it. So I got 4 HF and 4 HF right here. I've got C2H4 there and C2H4 there. What else do I have? Okay, I have carbons that are going to cancel, hydrogens that are going to cancel, F2 on this side and F2 on that side. Okay, so what I can do now, the only thing I haven't accounted for is the 6 F2s, but if you see right here, I have 4 F2s on the left side of this arrow, and I have 2 more F2s on the left side of this arrow. That means they're going to add, not subtract. So 4 plus 2 is 6, so that means I've accounted for that. So everything up here is accounted for. Now everything else should cancel. Oh, one more thing. And I actually did this, 2CF and 2CF. Okay, so everything that's circled is good. Everything else should cancel. So 2H2 on the right side of this arrow cancels with 2H2 on the left side of that arrow. Okay, cancel. 2 carbons on the right side of this arrow cancels with 2 carbons on the left side. Whoops, I should be putting X's through those. On that side. So everything either is X'd out or circled, so we're good to go. So that means our numbers are ready to be added. So we'll go ahead and do that. And we've got negative 1360 minus 1074 minus 52.3. And check my numbers. I did this pretty fast, but I get a delta H of reaction for that of negative 2,486 0.3. Okay, and it is for 1 mole, so that's what I got for that. So, okay, all right. So if you think my work is wrong, let me know, but I think everything seemed to work out there.